Hello, everyone. My name is Jeff Latansky. Welcome to Crosstalk Live, Leviton Network Solutions webinar series. Today's topic is reclaiming data center floor space, adopting centralized patching fields for efficiency and growth management. This 45-minute presentation will cover some current trends and techniques for addressing critical differences in network architectures, space management, and cost-saving measures, how traditional cabinet patching compares with patching in a centralized fiber distribution frame, and the range of link loss options and connectivity solutions. Our presenter today is Tony Ewan, a Senior Fiber Product Manager with Leviton Network Solutions. Tony has more than 13 years of experience overseeing the development and deployment of a wide selection of fiber patching solutions, including the high-density HDX fiber distribution system. He's an active member of BICSI and sits on several TIA cabling subcommittees. Tony?
Thanks, Jeff. Hello, everyone. Welcome and thanks for taking the time out of your busy schedule to attend today's presentation. My name is Tony Ewan. I'm a Senior Product Manager in the Fiber Connectivity Group of Network Solutions. I'm based out of Bothell, Washington, just outside of Seattle, Washington. And as Jeff mentioned, I've been with the company for over 13 years now. So this presentation will look into how having a centralized patching field or a main cross connect in your data center will look like, if it makes sense to do in terms of channel insertion loss budget, and how it benefits you as a data center manager if one of the criteria you look at in a data center is the cost of floor space or a loaded cabinet cost. So for today's agenda, I will start off with trends in the data centers. The sizes of data centers can be categorized in two types, enterprise and cloud data centers. Both types of data centers are continuing to grow to sustain the demand for greater bandwidth driven by mobile data, video streaming, cloud data, Internet of Things, broadband, and etc. The impact of these changes mean more and more fiber in the data center, specifically in the main distribution area over the next 5 years. How do you manage the cabling optimally, and what is the best return of infrastructure investments is discussed first in understanding the fiber loss budget at high speeds, and when I discuss how a centralized cross-connect patching field is the solution for managing fibers in the thousands. So, fiber trends in the data center. Continued migration from the traditional 3-tier to 2-tier leaf and spine architecture. Top of rack and centralized patching are top 1 and 2 architecture in the data centers. There is now clear distinction on or separation between enterprise and cloud data centers. Many traditional enterprise data centers are moving to the cloud or to co-location providers. Creation of next generation 25G ecosystem for higher speeds to complement 10G ecosystems. And lastly, new OM5 fiber type buzz that I will discuss in more detail. The 2-tier or fat tree architecture is also called a leaf and spine. The leaf and spine architecture addresses the challenges of a traditional 3-tier architecture and is becoming the standard for greenfield data centers. All access switches are connected to every interconnection switch and provides a redundant path. Traffic flows east-west, reducing latency between access switches. There is reduced cost, complexity, and power consumption. Very scalable fabric and are typically implemented in today's data centers. Impact by going with a leaf and spine architecture is that there will be ultra high density of fibers in the main distribution area that need to be better managed. In this slide here, BISRIA, a marketing and research agency, asks end users of enterprise and co-location data centers globally on what network topology they are using. As you can see, top of rack switching is utilized significantly in enterprise and co-location data centers, followed by centralized switching, which is essentially a centralized patching field. The benefit of top-of-rack switching are faster deployment of server cabinets, shorter trunk cable runs, and better management of oversubscriptions. The main architecture for hyperscale or cloud data centers is typically centralized switching to manage the thousands of fiber cables. In this slide here, provided by Deloro Research, you can see the growth of data centers. Data centers are characterized in this table as enterprise and cloud data centers. And as far as enterprise, they're small, medium, and large sizes, whereas cloud data centers are sometimes called hyperscale data centers. Each type of data center is characterized based on number of servers, number of customers, etc. takeaway here is that there are over 1 million customers for the enterprise, where there are less than 100 total customers identified as cloud. Top 7 cloud providers are your giants such as the Amazon Web Services, Microsoft, Google, IBM, etc. The graph on the right shows how cloud data centers will be continuing to grow in the next few years, as enterprise data centers will slowly decline due to consolidation and or moving to the cloud. This slide shows the transceiver market forecast for 8 data speeds provided by Light County Market Research. As you can see, 10 gig, the light brown color, represents the majority of shipments in 2017 and years to come. Growth of 100 gig, darker blue color, is expected to grow at a higher percentage than other speeds the next 5 years. Adoption of 400 gig is expected in 2019, but not growing as fast. Looking at the market forecast for 25 gig transceivers and higher speeds, shipments of 40 gig is looking at topping off in 2018, with 100 gig surpassing 40 gig in 2019. Adoption of 25 gig is expected this year and continue to grow for the next 5 years, as we see 25 gig to the server as being the main driver and a new ecosystem fiber lane succeeding 10 gig fiber lanes. This slide is a good visual to see what the current and future state of network configuration in the enterprise and cloud data centers. Currently in the enterprise data center, the speed down to the server is 1 gig and uplink is 10 gig. Future network speeds will be 10 gig down to the server and uplinks of either 40 gig or 25 gig. In all these cases, the fiber type used is either OM3 or OM4 multimode due to the short distance required. For cloud data centers, current network speed is 10 gig down to the server and 40 gig up. Future network speeds can be as fast as up to 100 gig down to the server and up to 400 gig uplinks. Cloud or hyperscale data centers, because of their enormous sizes and frequent refresh of active equipment, are typically using single mode fiber type. So this slide shows what the percentage of trunk lengths that Leviton shipped in 2016. As you can see, 91% of the trunk length is less than 50 meters, 98% is less than 100 meters. These length percentages in the 90% are reflective of what we see from other manufacturers as well. It's not coincidence that the majority of these fiber trunk length is less than 100 meters, which supports IEEE standards for multi-mode high-speed channel insertion loss. As for the fiber type, we sell more OM3 than OM4 currently. OM4 is continuing to grow each year, and we expect it to surpass OM3 in the next 5 years, as the price difference in the cables will become less of a significance. The last data center trend is the buzz with the new OM5 fiber type. A little background on this fiber type. Wideband multi-mode fiber, or WBMMF, is a new fiber medium specified in TIA 492 AAA-E and published back in June of 2016. Next, ISO IEC approved this new fiber type and specified a lime green color jacket for the cable. OM5 was created to support shortwave division multiplexing, or SWDM, between 850 nanometer and 953 nanometer for high data speeds. Call for interest have started in IEEE 802.3 to develop standards using SWDM for data centers that require greater link distances and higher speeds. All fine and dandy, but the current state of OM5 is very slow adoption in the market. The cable itself is about 60 to 90% premium over OM4 fiber, which would scare anybody. If greater link distance is needed, enterprise IT and data center managers are increasingly adopting single-mode fiber systems to solve their challenges. Single-mode transceiver prices are continuing to drop thanks to hyperscale data centers buying in large volumes, creating a more cost-effective solution. In the next session, I will look into fiber loss budget for 2 and 4 connection at high data speed for multi-mode. Multi-mode is still the most cost-effective solution for data centers with trunk lengths of less than 100 or 150 meters. 90+% of fiber trunk lengths are less than 100 meters, as you saw in previous slide. Here's a graph from Ethernet line showing the evolution of Ethernet speeds starting back in 1983 with 10 meg. Ethernet speeds were evolving by a factor of 10 until the introduction of 40 gig in 2010. and soon to be 400 gig in 2017. Just this decade alone, there will be a number of Ethernet speeds introduced that supports a specific application need or demand. These are just IEEE standards that are published or will be published. Besides these IEEE standard groups, there are a number of multi-source agreements, or MSA, that are in development by equipment vendors in developing form factors for communication interface. This slide is an overview of 40 gig optical transceiver as of August 2017. As you can see, there are 12 listed and there are more in development. I'm not going into detail of each, but I want to highlight a couple of things. Of the 12 transceivers, only 4 are IEEE compliant and the rest are MSA or it is proprietary. Of the 4 IEEE compliant transceivers, there are 2 multi-mode and 2 single-mode fiber types. Having IEEE compliant ensures interoperability and interconnectivity with other manufacturers. Looking at 100 gig optical transceivers, there are 11 listed here, and again, 4 are IEEE compliant, 2 each for multi-mode and single mode. A lot of choices here, same with 40 gig transceivers that you need to be aware of when designing a data center. Unless you're working with a specific equipment vendor like Arista, Juniper, or Cisco, the safest choice is go with an IEEE compliant design. This is a great table with a lot of information speaking to the attributes for each respective IEEE Ethernet multi-mode speed. Single mode is not presented just because multi-mode is still a very cost-effective solution for enterprise data centers that require short distances, as I mentioned earlier. If you recall from what I said earlier, 10 gig will continue to be dominant data speed in the next few years, with 100 gig growing at a higher percentage than 40 gig. This is where it is important to design your data center to be flexible and scalable in order to migrate from 10 gig to 40, 100, and even 400 gig. At minimal, you should be specifying OM4 fiber type that will get you a distance of 100 meters. 400 gig base SR16 is expected to be published at the end of this year, and many manufacturers believe there will be minimal adoption due to the high number of fibers required with a new MTP-MPO connector. Expected in 2018 are new 50, 100, and 200 gig standards that will most likely see adoption earlier and lessen the need for 400G base SR16. In the next few slides, I will show illustrations of 2 and 4 connection points channels starting with 10 gig and a migration path up to 100 gig. The calculated channel insertion loss would be compared to IEEE standard at max distance to see if channel passes or not, based on Leviton's component insertion losses. In this slide here, I'm illustrating 2 connection points with MTP to LC cassettes. Technically, there is 4 mated pairs, but topology-wise, it is 2 connections or 2 reference points in the channel. The backbone trunk cable connecting both cabinets reflect a 12-fiber MTP trunk with cable attenuation of 3 dB per kilometer. Leviton's Unity MTP to LC cassettes are 0.35 dB insertion loss. LC patch cords are used to connect from MTP cassettes to the switches. On the switches, it is SFP plus transceivers form factor that the LC connectors plug into. The calculated channel loss based on the 2 connection points and backbone cable is 1.6 for OM3 and 1.9 for OM4, both under the IEEE max channel insertion loss with plenty of headroom. In this 4 connection point 10 gig channel, a centralized cross-connect patching field cabinet is added. I will talk more about the benefits of having a centralized patching field later in this presentation, but in general, the patching field cabinet provides a solution to easily manage ultra-high density fibers in your main distribution area. In the cabinet, there are 2 19-inch fiber enclosures representing the incoming trunks from the switches at each end of the channel. LC patch cord connects or patches the 2 links together. With a 4 connection point, the calculated channel loss is under the IEEE max channel insertion loss for both OM3 and OM4 fiber type, as you see here. Migrating from 10 gig to 40G SR4, MTP LC cassettes are replaced by MTP to MTP conversion cassettes as one option. Instead of conversion cassettes being used, MTP pass-through adapter panels can be used in combination with MTP array cords, which I will show in the next slide. One benefit of using a conversion cassette is that all the fibers in the trunk cables is 100% utilized, meaning no dark fibers. 8-fiber array cords identified by gray color boots are used to connect from the conversion cassettes to the switch. On the switches, it is QSFP plus or CFP transceiver form factor that the MTP connectors might plug into. Calculated channel loss budget passes for both OM3 and OM4 fiber type, as you can see here. For this 4 connection point 40 gig SR4 channel, MTP pass-through adapter panel replaces the MTP conversion cassettes. Calculated channel loss budget passes for OM3 and OM4, as you can see here. If you're wondering if MTP conversion cassettes can be used here instead of the MTP adapter pass-through panels, the answer is no. At max distance, the calculated loss budget would be 2.3 for OM3 and 1.9 for OM4. So migrating from 40 gig to 100 gig SR10, the conversion cassettes are replaced by MTP pass-through adapter panels, or there are no replacement needed if the MTP adapter panels were already installed for 40 gig. 2 12-fiber MTP array cords are used to plug into the QSFP28 transceivers and into the switch. Calculated channel loss budget passes for both OM3 and OM4 fiber types with plenty of headroom. In this 4 connection point 100 gig SR10, the traditional cabinet is replaced by Leviton's fiber distribution frame as a centralized patching field. The HDX frame, which I will talk more later, is open access from the front and rear and simplifies cable management. Calculated channel loss budget passes for both OM3 and OM4 here again. In this illustration of a 2 connection points, 2nd generation 100 gig SR4, the cabling follows the same structure as 40 gig SR4. Instead of 10 gig fiber per lane, it is now 25 gig fiber per lane. Using MTP pass-through adapter panels, the calculated channel loss budget passes for both OM3 and OM4 fiber types. If using MTP conversion cassettes, the calculated loss budget will pass for both OM3 and OM4 too. With 4 connection points for 100 gig SR4 channel, the calculated losses all pass, as you can see here too. So summary of budget losses at high data speeds. First and foremost is always design your network to be flexible and scalable for future migrations. Market research shows that active equipments are refreshed every 3 to 5 years. For enterprise data center, it may be more like 5 to 7 years. Having a flexible and scalable cabling solution minimizes ripping out old fiber cables. Design your network based on IEEE standards to ensure interoperability and interconnectivity amongst other manufacturers. Leviton's Unity solution passes all calculated 2 and 4 point channels. Hopefully we can maybe sway some of you data center managers or IT managers to maybe looking at a 4 connection point using a centralized patching field. So let's get started here. So this is a simple layout showing a main distribution area that serves the storage area network, storage mainframe, core LAN network, equipment distribution area. In a centralized patching field, the optical distribution frame or cabinet is away from prime data center floor space and provides optimal flexibility in managing the networks. So benefits of a centralized patching field as a main cross connect. Typically, solutions are traditional cabinet or open frame with no active equipment inside. A traditional cabinet maintains a consistent look throughout the data center with cabinets. Open frame solutions are typically used in central offices where there are tens of thousands of fibers that are being managed, but we are beginning to see a place for them in the medium to large and hyperscale cloud data centers. With a centralized patching field, there's a minimal need to access cabinets that house high-dollar assets like switches, storage devices, routers, making them more secure and minimizing risk of damage or downtime. The centralized patching field should replicate the switches or respective equipment device port for port, making moves, adds, and changes structured, easy to access, and scalable. The centralized patching field does not have to be centrally located, like how it was shown in the last slide. The patching field does not require power or cooling, so it can be located away from all the active equipment in its own floor space or isolated in a separate room. The premium floor space of a data center can and should be utilized for revenue-generating cabinets, housing switches, and servers to maximize your return of investments. Having a structured and centralized patching field will lower operating expenditures by reducing time for refresh of equipment when migrating to high speeds, when upgrading software as needed, and when performing maintenance when needed. Traffic can be easily redirected at the patching field while the equipment are being serviced or changed out. Looking at features of a traditional cabinet solution, data center managers typically might spec 1 or 2 cabinet sizes for the same consistent look throughout the data centers. Cabinets are typically sold without vertical or horizontal cable managers, so you would have to piece together a solution, but there are some cabinet manufacturers that do make to order. Cabinet sizes vary in sizes in terms of width and depth and can take up to 4 floor tile spaces. Typical height is 7 feet tall with 42 rack units of usable space. If there are no height restrictions, you can see up to 8 feet tall cabinets with 48 rack unit space. Cabinets are typically listed under UL 2416, which meets new UL requirements for equipment cabinets. So what does a fully loaded cabinet look like with fiber enclosures or panels, and what are the challenges you might ask? When installing fiber enclosures or panels in a cabinet, you're looking at about 36 usable rack unit space out of a 42 RU cabinet. 6 RU of space should be set aside for horizontal patch cord cable management. Enclosure density can range from 72 to 144 fibers per rack unit. The higher the density, the more challenges you have in managing and accessing patch cords. 96 fibers per rack unit is an optimal density, which means you can accommodate up to 3,456 fibers in a cabinet. Picture to the right shows how the enclosures or panels will replicate the core and edge switches and how patch cords may be routed between the two. Challenges with a cabinet solution with various lengths of Challenges with a cabinet solution are various lengths of patch cords needed, minimal slack management within cabinet, tight fiber bend radius concerns, and moves, adds, changes are not easy to do. A new but old technology of centralized patching solution is an open fiber distribution frame. Leviton HDX frame is typically what you would see in a central office or service provider head-end. This is a Leviton design solution manufactured and assembled in our headquarters in Bothell, Washington. Complete open access in the front and rear of the frame with integrated vertical and horizontal cable management. The frame stands 7 feet tall and occupies 1 2x2 floor tile space. Fiber density is 3,168 fibers for LC and 15,552 fibers for MTP or MPO connectivity. It is the highest density per square feet for an open frame solution. Comparing the space savings between a cabinet and HDX frame, a 32-inch wide by 48-inch deep cabinet is about 11 square feet, whereas the HDX frame is about 4 square feet. 10.7 minus 4 equals 6.7 square feet of space savings. You can easily see how much space savings will add up as you have more cabinets utilized. So back to our HDX frame solution. A frame can accommodate up to 22 2RU modular patch decks that can hold up to 144 fibers. Only one length 3-meter patch cord is needed to patch within the frame. If you go in between frames, you still only need one length 5-meter patch cord to do the job. Patch cords are bundled together in this open design, which makes it easy to manage and do moves, adds, and changes, and eliminates any tight fiber bend radius. The frame solution is designed for easy migration from 10 gig to 40 and 100 gig. The table here shows the migration path and density for each configuration. Starting with 10 gig using MTP to LC cassettes, the max fiber density again is 3,168 fibers or 1,584 10 gig channels. With the small physical footprint, the density per square feet equates to 452 10 gig channels per square feet. That's the highest density per square feet for an open frame. As you read from left to right, you can see what the density per square feet are for 40 and 100 gig if you go in with a 12 or 24 fiber MTP connectivity. Here's a summary table listing key features and how a cabinet compares with the HDX frame. As you can see, there is more benefits in going with an HDX frame solution, as you can see here. To help you determine how much space savings you can realize for your project or data center, Leviton have created a return of infrastructure investment tool comparing traditional cabinet versus the HDX frame. This tool is located on our website. You can start by inputting what the cost is per month for 1 square feet of data center floor space. Default right now is set at $50. Next, you enter the size of the cabinet being used and then input all the devices or zones that will be cabled back to the cabinet. There are assumptions that are made with this tool, and one of them is that the enclosure density installed in the cabinet is 72 fibers per rack unit for the very ease of managing patch cords. So in this example of a small and medium-sized data center, you can see the inputs in the bullets that shows the number of fibers for core switch, director switch, storage switch, and server cabinets. The tool will calculate how many cabinets or frames required, total square feet needed, and first year cost and floor space. In this scenario, the HDX frame shows that you save 42.9 square feet or $25,710 in space savings. In another example, for a large data center design, you can see the inputs in the bullets. In this scenario, 20 cabinets are required versus 12 HDX frame. There is 165 square feet space savings, equating to 103,000 savings in the first year. That's a lot of money saved that can be invested in revenue generating floor space. Now, this tool is not a guarantee of true space savings, but a good reference point. You always want to check out this tool. Please check out our tool on this website for yourself and see if it makes sense for your project or your data center. So a summary of centralized patching field. First and foremost, again, always design your network to be flexible and scalable for future migration to higher speeds. I reiterate here again the key benefits in going with a centralized patching field. If you're designing a data center now in which you need to manage over 4,000 fiber, then you should look at a centralized patching field, whether it be a cabinet or a HDX frame.
On behalf of our presenter, Tony Ewan, I'd like to thank you for attending Leviton's Crosstalk Live webinar today. Everyone, thank you very much for your time.
Thank you, everyone.